Hi, hello everybody. Welcome back to Annual Academy. This is me, Ankita, and today's topic is periodic properties. One among the periodic properties, which is effective nuclear charge. Okay, so let's start. So what do you mean by effective nuclear charge? So effective nuclear charge actually means the actual charge which is experienced by the electron. What do you mean by actual charge? So let me say, let's say you have a nucleus, and surrounding this nucleus, you have one electron. Okay, so this is our electron. Now, what is happening over here? The nucleus, which is positively charged, will experience some kind of force of attraction towards the electron, which is negatively charged, correct? So this is an electron, which is going to be negative in charge. So there is only a force of attraction between the nucleus and the electron. There is only one electron surrounding the nucleus, and hence the effective nuclear charge, which is represented by Z effective, this is the subscript, Z effective, which is the effective nuclear charge, that is going to be equal to the nuclear charge. Okay, nuclear charge means it depends on how many protons are there. So let's say that you have one proton over here and you have one electron. This is a typical case of hydrogen. So the nuclear charge is simply the atomic number itself, which is equal to 1. Okay, why? Because you have one proton and the effective charge which is experienced by the electron will be completely due to the force of attraction by one proton. Okay. Now let's move to another case when you have helium. Helium. So in helium, you have two electrons and two protons. So the Z value actually is equal to 2 because it has got two protons. It has got two protons. And the Z value, which is the nuclear charge, Z is just the nuclear charge. Nuclear charge corresponding to the number of protons, and that is just 2. But here, the effective nuclear charge is not equal to the total nuclear charge, which is equal to 2. I'll explain why. Why? Because already the nucleus will show force of attraction towards the electrons. That is there. Positive will attract the negatives. That is definitely there. But apart from that, these electrons will experience electron-electron repulsions. So due to the electron-electron repulsions, the actual charge, Z effective, is less than the nuclear charge. How much low is it? We'll be learning. So one of the factors wherein this effective nuclear charge changes its value is because of the electron-electron repulsions. There are other reasons also. Let's say you have a nucleus. And now let's say you have 3 electrons. So you have 1, 2, and 3. 3 electrons are there. And you have 3 electrons, you have 3 protons. Now let's say the total nuclear charge is equal to 3 over here. Now what you can see is already there are 3 electrons. So definitely there will be electron-electron repulsions. Apart from that, you can see another factor which is called shielding. How does shielding happen? Shielding happens because, see, this electron, which is there in the outermost orbital, is shielded by these 2 electrons. Let me number 1, 2, 3. So, the third electron cannot fully get the attention of the nucleus. Why? Because there is a shield in between. There is a shield in between. And hence what happens is the nucleus cannot completely give its forces of attractions at the third electron. That is because of the shielding. So another reason for reducing the effective nuclear charge is shielding. And the shielding varies with each shell. Okay, shielding. So these are the two reasons. So again, because of these reasons here also, the Z effective is not equal to 3. It is actually less than 3. Okay. So how do you determine the effective nuclear charge? Is by a rule which is called the Slater's rule. So this rule is not that common in the question papers of CSIR-NET, but then you get a lot of questions for other exams like BARC or some other state level examinations and all. Okay. So actually, the way you can find the effective nuclear charge is simply the nuclear charge minus the shielding constant. What is, I hope you understand what is nuclear charge. Nuclear charge is simply the atomic number. Simply the atomic number. And sigma over here is the shielding constant, or you can call it the screening constant. Everything is the same. Screening constant. So Z effective is always less than Z when it is more than one electron. If it is one electron means, you know that Z effective and Z is the same because there are no electron-electron repulsions, no shielding, everything is okay. Okay. Now, you have to learn something called the Slater's rule. Okay, this session is entirely going to be problematic. Problematic in the sense we'll be solving a lot of questions in that sense. So the first note over here is where students make mistake. When you apply the Slater's rule, write the electronic configuration. Please note it along. Write the electronic configuration in increasing order of n value. Increasing order of n values. Very important. Very important. Okay, we'll do problems wherein you have to be careful of this rule. Let's start with simple questions now. Let's start with very easy questions now. Okay, so we have to learn several cases. So the case 1 is when if electron is present in S or P subshell, you have to learn an equation wherein the screening constant is equal to number of electrons in nth shell minus 1 into 0.35 plus number of electrons in n minus 1th shell into 0.85 plus rest of the electrons into 1. This is how you calculate the screening constant. Okay, so here also you have to pay attention. They are asking about calculating if electron is present in the S or P shell. You will understand why I stressed on this towards the later end of the session. So let's start with the question. Question number 1. Find the effective nuclear charge on 1s electron of hydrogen. So to know this, first of all, the first thing is you should be thorough with the previous lecture wherein we learned how to write the configuration. Very easy. Z is equal to 1 over here. Electronic configuration is 1s1. There is no screening, no shielding, and hence the shielding constant is 0. Shielding comes into play, the effective nuclear charge changes from the actual nuclear charge only when there are more than one electrons. So here there is only one electron in hydrogen, correct? So the screening constant is equal to 0 and Z effective is equal to Z minus sigma is the formula. So effective nuclear charge is equal to 1. Easy. Effective nuclear charge is equal to 1. Okay. Second, Z effective on 2s electron of, let it be 1s itself. 1s electron of helium. Let's say helium. So when you have helium, understand that here Z is equal to 2, more than one electron is present, electron-electron repulsions will come, because of which there will be a value of screening constant. What is the configuration? 1s2. So there is only one shell, which is the nth shell, and your formula for screening constant is number of electrons in the nth shell, which is 2, minus 1 into 0.35. That's it. Nothing else. Correct? So that is equal to 0.35. So this is your screening constant. This is your screening constant. What you have to find is your effective nuclear charge. How will you find that? Effective nuclear charge, Z effective is equal to 2 minus 0.35, which is equal to 1.65. Okay? I hope you understand how did this come. Here, there is only one shell. N is equal to 1. You will get to understand when we do further problems. 3. Z effective of electron in 2s of lithium, let's say. 2s of lithium. Okay. So for lithium, Z is equal to 3. What is the configuration? 1s2, 2s1. Okay. Now understand that over here, the value of N that you have is always the highest shell. So here it is N is equal to 2. This is N and this is N minus 1. So how many electrons are there in N? There is only one electron. And what is the equation? 1 minus 1 into 0.35. In N minus 1, there are 2 electrons. No, it's just 2. No minus 1. 2 into 0.85. And there are no rest of electrons. Everything is counted. So this is 0 plus 2 into 0.85, which is 1.70. This is the value of the screening constant. So Z effective is going to be 3 minus 1.7, which is equal to 1.3. Okay. I hope you get it. Try beryllium. Try beryllium. Z effective of electron in 2s of beryllium. So see, beryllium is Z is equal to 4. Configuration is 1s2, 2s2. Now identify the value of N. This is N and this is N minus 1. Only that much is there, correct? So number of electrons in N minus 1 into 0.35 plus N minus 1 has got 2 electrons into 0.85 plus there are no rest of the electrons. That's it. So 0.35 plus 1.7 is your effective screening constant. This is 2.05. 2.05, correct? Then Z effective is going to be your value Z minus screening constant, which is 4 minus 2.05. That is 1.95. Can you see the scenario? You took beryllium. Here there is 1s and here there is 2s. So 1s has got 2 electrons. 2s has also got 2 electrons. So one of the electron in 2s is actually supposed to feel the strength of all the 4 protons, but it is feeling only 1.95. This is a takeaway. It cannot feel the forces of attractions of all the 4 protons. Because of the electron-electron repulsions, because of the shielding and other factors, it can feel only 1.95. Okay. Let's continue with boron. So Z effective on electron in 2p of boron. Now pay attention over here. Z of boron is equal to 5 and that is 1s2, 2s2, 2p1. Now identify the n value over here. N is equal to 2 and you have to consider the electrons in all the types of orbitals. Not only 2p, 2s also. This is n. This is n minus 1. Are you getting my point? It's not only 2p. You have to take 2s also because I said shell, not subshell. It is the nth shell. So you have to consider all the subshells within the same number. So 2s and 2p also should be considered. Okay? So how many electrons are there? In n, 3. So 3 minus 1 into 0.35 plus 2 into 0.85. No rest of the electrons. That's it. So 2 into 0.35 plus 1.7 is your screening constant. Correct? This gives out to be, I have calculated 2.4 and your Z effective will be 5 minus 2.4, which is 2.6. 2.6. Okay, just for practice, please do carbon as well. Carbon. Z effective on electron in 2p of carbon. Okay, so carbon is Z is equal to 6. Configuration is 1s2, 2s2, 2p2. So these many electrons are there in the nth shell. Only this much of electron is present in n minus 1th shell. Correct? All right. Please start the calculation. So this is 4 electrons in n. So 4 minus 1 into 0.35 plus 2 into 0.85. That's it. No rest of the electrons. So 3 into 0.35 plus, let me calculate. I haven't calculated it. You get 2.75. 2.75. And the Z effective would be 6 minus 2.75 and that is 3.25. Okay. I hope you have got an idea of how things are done. Okay. I think now it is easy. We'll do one more with 3 in it. Let's do sodium. Sodium. Find the Z effective of electron in 3s of sodium. Okay, so sodium is Z is equal to 11. And when you write the configuration, it is 1s2, 2s2, 2p6, 3s2. Sorry, 3s1. It's 11. It's 11, 3s1. Right. So when you have this, identify this is n. These many belongs to n minus 1 and these are the rest of the electrons. Okay. So when you do this, Start the calculation, please. So your effective constant is number of electrons in N is 1 minus 1 into 0.35 plus in N minus 1, you have 8 electrons. So 8 into 0.85 plus rest of the electrons, you have to add them all. You have only 2. So 2 into 1. Okay, so 0.85 into 8 is 6.8 plus 2, which is equal to 8.8. And your Z effective is only 2.2. 11 minus 8.8 is 2. I hope you're getting it. Right. Okay. Now let's say that I give you a configuration like 8. Here only, let's say that the question is to find the Z effective of electron in 2p of sodium. Pay attention, 2p of sodium. It is sodium only, but not 3s, 2p. So again, we know Z is equal to 11. Configuration is 1s2, 2s2, 2p6, 3s1. So you have to consider the effective nuclear charge felt in one of the electron, which is in the second shell. So whoever is there after the shell that you consider in the question, these won't participate in shielding. Doesn't that make sense? Does not participate in shielding. Isn't that true? See, you have 1, 2, 3. Okay. If you have an electron in the second shell, the forces of attraction by the nucleus is shielded by the first shell only. The third shell is not shielding the second shell. Okay. So the electron which is there in the third shell, the electron which is there in the second shell is shielded from the nucleus by the first shell. So if the question is to find the Z effective of 2p of sodium, even though it has 3s, you need not consider that. Do not consider this. You start from here. So this is N and this is your N minus 1. Got it? Yeah. So again, this gives us 8 minus 1 into 0.35 plus 2 into 0.85, and that's it. There are no rest of the electrons. So you have 7 into 0.35 plus 1.7, which is equal to 4.15. And your Z effective is equal to 11 minus 4.15. 6.85. I hope you get it. Okay. Let's do one more problem. If the question is to find the Z effective of electron in 1s of sodium, what you have to understand is this is 1s2, 2s2, 2p6, 3s1. You have to consider the screening of 1s and none of the shells after that. I'm talking about the shells. None of them will participate. So this is neglected. You have to consider only 1s2. So this is equal to 2 minus 1 into 0.35. Which is 0.35. But then please write a note over here. Note. Important note. It was said that if you consider it on 1s, only for, this is an exception, only for 1s. Note, to calculate in 1s subshell. Okay. in 1s subshell of any atom, it is actually equal to number of electrons minus 1 into 0.3. So see, always in 1s2, it is always going to be 2. So instead of taking 2 minus 1 into 0.35, what Slater said is, as it is very close to the nucleus, you need not put a value of 0.35, only put 0.3. This is a note. So just note it down, and here what you have to write is 2 minus 1 into 0.3. Okay. So your Z effective on sodium would be 11 minus 0.3, 10.7. Similarly, we did a question on beryllium as well. Make that correction. I didn't explain it there because that might confuse you. So if it is just 1s2 instead of 0.35, you're supposed to take only 0.3. Okay? Supposed to take only 0.3. Important because it is 1s. This is applicable only on systems where they ask about 1s. 1s. Okay. Let's say the question is on zinc. This is the 10th question. Zinc. Okay, so the question is, find Z effective of electron in 4s of zinc. Okay. So when this is done, again, mark this question as important. You will understand why. For zinc, Z is equal to 30. Configuration is 30, right? 1s2, 2s2, 2p6, 10 over, 3s2, 3p6. And we know that among 3d and 4s, here n plus l is 5, here n plus l is 4. So this will fill first. 4s2, 3d, 10. Okay. This is your electronic configuration. And when you consider this electronic configuration, the question is to find the Z effective on 4s. And you might think that we have to cut this because this is written afterwards. No. That is the note which we first wrote. See? Write the electronic configuration as increasing values of N. So this is the actual electronic configuration. And then you have to rearrange. You have to write it in increasing order. 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, and 4s2 is what you have to write. Okay? So now this is N, all the subshells of 3. This is N minus 1, and all of these will go to rest of the electrons. So what is the value of the screening constant? 2 minus 1 into 0.85, sorry, not 85, 0.35 plus 10 plus 6 plus 2, 18 into 0.85 plus rest 10 into 1. Let's try it out. So total, we get 25.65. Okay. And Z effective is going to be 30 minus screening constant, which is 4.3. I hope you get it. This is the note, very important. Which is very important. Now, all of these things which we learned was to find the Z effective on the electron. See, on electron, on the electron. Now let's say that instead of finding the Z effective on the electron, it is on the periphery. Meaning, let's say you have a nucleus, you have a shell, there are 2 electrons. Instead of finding the Z effective on any of these, you have to find the Z effective at the boundary, at the periphery. The equation is different. Okay, so please write it down. Effective nuclear charge on periphery, or it can also be called the boundary, is, it's very easy. Okay, if you understand the concept, it is very easy. It is number of electrons in nth shell into 0.35 plus number of electrons in n minus 1th shell into 0.85 plus rest of the electrons into 10. That's it. The only difference is over here. Number of electrons in nth shell into 0.35 minus 1 is not there. That's all. Okay, I'll explain why. Why? Because let's take 2 scenarios. I'm taking boron, let's say, which we have already done. So boron is, let's take beryllium. Okay, beryllium is 2s2, 1s2, 2s2. If you have to find the Z effective on this electron, how many electron-electron repulsions are there? By 1, 2, and 3. So in total, there are 4. But if you want to know the screening constant on this particular electron, there will be effect by the other 3 only. And that's why in the equation we have n minus 1 into 0.35. I hope you get it. This electron will not have electron repulsion with itself. Correct. It will have electron repulsion with the other electrons. So we have to subtract 1. But if it is not on the electron, if it is on any of the boundaries, we have to find, let's say this is the boundary. If you have to find the screening constant at the boundary, now how many electrons are there? 1, 2, 3, 4. You have to consider all the electrons in the particular shell. Okay, this particular shell. I hope you get it. That's why you don't take minus 1. Is that clear or did I confuse you? I'll explain it again. Let's say you took beryllium. You have 2 electrons here in 2s. And the equation actually is 2 minus 1 into 0.35 plus 2 into 0.85. If it is on the electron, you have to find the screening constant on the electron. But what we wrote over here is instead of the electron, if you have periphery, the same beryllium, if you have the periphery, let's say this is the boundary, and you have to find the Z effective of the boundary, then you don't do this minus 1. Okay, all you have is 2 into 0.35 plus 2 into 0.85. So why did we subtract this 1 over here? Because this electron will not repel itself. The electron repulsion, this particular candidate is excluded from the 4 electrons. Okay, so other 3 are considered. Those 3 are here 1 you have and here 2, 3. Here it's not like that. At the boundary, all the 4 electrons will repel and hence all the 4 electrons are to be considered. Okay. I hope it is clear. So you learn the equation, that's it. So this is something we have already done. This is 0.35 plus 1.7 and that is 2.05. Here what you have is 0.35 into 2, 0.7 plus 1.7, right? Which is 2.4. Okay, so this is the difference in the screening constant. And hence the Z effective will also be different. Here it will be 1.6. Here it will be 1.95. Okay. So this is about the Z effective on the electron or at the periphery. Now, instead of S and P, you can also get question from D or F. That is case 2. If electron is present in D or F subshell, okay, it's very easy. Screening constant equal to number of electrons in D or F subshell, whatever the question is, -1. We have to do -1 because now we are considering it on the electron, not at the periphery. Okay. Into 0.35 plus rest of the electrons into 10. Sorry, into 1, not 10, into 1. The earlier equation also I wrote 1 only, no? The main equation, yes. Yes, into 1. Easy. All right, so let's try out 2 questions. Note down the question. Calculate the Z effective on 3D electron of zinc. All right, so let's start with the configuration. Zinc is atomic number 30. So configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Right? Now in Slater's rule, we know that while calculating the Z effective, we have to arrange it in increasing order of n. So this becomes 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2. Now they have asked us to find the Z effective on 3D. So 4s2 need not be considered because that is a subshell which is outside 3D. Right? Now let's write the formula. The screening constant is equal to number of electrons in D or F subshell. Please pay attention. In the earlier case, it was nth shell -1. Here it is a number of electrons in the subshell -1. Okay, so how many electrons are there? There are 10 electrons. 10 minus 1 into 0.35 plus rest of the electrons. Okay, so that is how much? So you have 6 plus 2, 8 plus 10, 18 into 1 it is. All right, so this is equal to 21.15 and Z effective is equal to, actually it was 30, correct? Minus 21.15 it is, which is equal to 8.85 only. So one of the electrons in the 3D can feel only 8.85 units of the strength of the nucleus. Actually, it has got 30 protons, but it can feel only 8.85. Okay, one more question. Calculate the Z effective. Effective on 3D electron of manganese. Try it on your own, please. Manganese, when arranged in the increasing order of N, Z is 25. Okay, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. They have asked us to find the Z effective for 3d electrons, so 4s need not be considered. How many electrons are there in D? 5 minus 1 into 0.35 plus remaining there are 18 electrons into 1 it is. Okay, so 4 into 0.35 plus 18 gives us a screening constant of 19.4. So the Z effective over here is going to be 30 minus 19, not 30, 25 minus 19.4, which is 5.6. Okay? All right. So that's all for this session. See you in the next.